Hello and welcome back to the Prince William Sound Natural History Symposium. Again, my name is Heather and I'm your host for this last session. We have two more presentations. Our next presenter is Louis Sass, who will give an overview of the current state of Alaska's glaciers and how they're shrinking and what this means for all of us. Again, please put your questions in the question box down below. And if you have any comments, those can go in the chat box and we'll do our best to keep an eye on those. Louis Sass grew up in the snow and mountains as a kid in Colorado. He worked as a mountaineering instructor and climbing guide for 12 years before going back to school to study glaciers. He received a master's degree from Alaska Pacific University studying the Eklutna Glacier and started working for USGS in 2008. He now runs the operations and safety side of USGS's glacier project. And on good days, he even gets to do a little bit of science. Welcome, Louis.
Thank you, Heather, and thanks everybody for being here. Can you hear me?
Yep, loud and clear.
Yeah.
And
great.
See your screen too.
Okay. So I feel pretty lucky to be able to study glaciers in Alaska. We get to spend a lot of time in a pretty spectacular landscape up here. I really like this cartoon, partly because it's true. We do not study charismatic megafauna. They're not like little warm fuzzy things. But glaciers really do define the Southern Alaska landscape. And they're a pretty important part of the overall ecosystem up here. So this afternoon, we'll talk a little bit about the regional status of glaciers in Alaska, and then from there, we'll mostly talk about the different projects that USGS is working on and what we're doing up here. So over the past really 10 to 12 years or so, it seems like every time I turn around, there's a new paper out that talks about how important the changes are in Alaska. And overall, Alaska has one of the largest groups of glaciers outside of Antarctica and Greenland, anywhere on the globe. So one of the largest areas. And the changes, the rates of change on those glaciers are among the very fastest. And so what that means is that Alaska glaciers really are sort of the biggest losers. They're the biggest single area of mass loss outside of Antarctica and Greenland. And that's true kind of no matter how, like what methods you use, what data you look at. Here's a new paper that just came out a couple weeks ago, using completely different data than that previous paper by Zemp, different methods, and they're coming to the exact same conclusions. So there's really sort of increasing consensus that not only does Alaska have a lot of glaciers, but they're changing really, really rapidly. So I kind of cropped out some of the glaciers up in the Brooks Range. They're pretty small compared to what is going on here in Southern Alaska, but the Alaska region overall has about 86,000 square kilometers of glacier. And that is a little bit bigger than the 6 smallest states combined. It's about a third of the area of the Great Lakes, or a little bit larger than Lake Superior. And if we just think about the last 20 years, glaciers in the Alaska region have lost 3/4 of a meter of water on average over the whole area per year. So that's more than 50 feet of total water during that time since 2000. So that'd be like if we drained 50 feet of water out of Lake Superior over that time frame. And all that water has to go somewhere, and especially in a place like Prince William Sound, but really anywhere in Alaska, the water just is not very far away from the ocean. This little plot is from well, it highlights some work that was done a couple of years ago that bold black line is a hydrologic model that takes into account glaciers directly. So we're just looking at the runoff into the Gulf of Alaska here. and we're estimating what that runoff is with a hydrologic model. And the older models didn't really explicitly account for glaciers and didn't really understand how glaciers worked, or didn't account for them at least. It wasn't until 2016 this guy Jordan Beamer came along and he said, whoa, you know, the circulation that we see in the Gulf of Alaska can't really be explained by those old models. What's going on? And he said, oh, it's because of the glaciers. We've got this huge amount of water. It's very fresh, it's very cold, and it has really distinct sort of chemical and physical properties. And it's coming in to the Gulf of Alaska all in the middle of the summer. So I want to step back for a second and just think about how glaciers work. And even before we even talk about glaciers, let's just think about how rivers work. So on a river, say like the Yukon River, you get a couple of really nice, hot, sunny days on the interior side of the St. Elias Range and the Coast Mountains in northern southeast, and you get a bunch of melt that comes off the glaciers up there. It hits the upper part of the headwaters of the Yukon River, and the river comes up a little bit. And we can predict how long it's going to take for that water to get all the way down to Amonik on the coast. And we can know how much it will actually impact the water levels down at Amonik with a great deal of precision. And the reason we can do that is not because we understand the physics of the water flow around every single bend of the entire river, where we try to solve that problem. It's because we've seen it 100 times before, and we have a simple statistical fit. So we've seen it happen a bunch of times, and we can just say, oh, this is what it looks like. Glaciers are more complicated because they flow a lot slower. And so that response to climate takes time. So this little schematic I've drawn on the screen, that lower black line is the bed of the glacier. This is a cross section. That top black line is the surface of the glacier. If we think about what happens in the winter, we get snow on the whole glacier, more snow up high, usually less or maybe even none at all down at the bottom of it. Then in the summer, we melt some of that snow off, and we melt more down low and we melt less up high. So up high on the glacier at the end of the summer, we have a little bit of snow that's left. Down low on the glacier, we don't have any snow left and we've lost some of the ice. So we can think about that as a mass balance where we have accumulation up high, we've got the stuff that's added, and we have ablation down low. In between those two zones, we call it the equilibrium line altitude. It's sort of a theoretical construct. And so you've got the accumulation zone up in the top, and you've got ice flow underneath the ELA, and then it flows down to supply the terminus, which is continually melting away. And so if the glacier is in equilibrium, the amount of subsidence in the upper glacier that's replenished by new snow is equal to the amount of flow through the middle of the glacier and is equal to the amount of melt that happens at the bottom of the glacier. If the ELA climbs up, say due to a changing climate, but accumulation zone gets smaller, we have less flow through the glacier and the ablation zone's bigger. And so the amount of flow can no longer supply that whole ablation zone. And so some of the ablation zone actually melts and the terminus retreats back. The other thing that tends to happen on most of these glaciers is as you decrease the flow, the glacier tends to thin. And sometimes that thinning is really important because it actually decreases the amount of accumulation zone even further. And then you have feedback between that change in surface elevation and the mass balance. And so you have even less area for accumulation, and the terminus has to retreat back even further to come into equilibrium with that. So that's kind of how glaciers work at the most basic level. Now I want to transition and tell you a little bit about our program here at USGS and some of the work we're doing. So the Benchmark Glacier program studies 5 glaciers in Western North America in detail. And Wolverine Glacier is the blue one in that middle figure right up here. And it is in the western edge of western Prince William Sound. It's just above the top of Nellywan Fjord and Kings Bay. And so we have sort of three main tasks at those glaciers. And I'll talk a little bit about each of those and some of the other science that's happening. So mass balance accumulation, the most basic way we study that is through a really simple thing. We go out and we dig snow pits every spring and every fall, and we sample those snow pits and we weigh the samples. Of course, most of you are probably familiar that as you get up to higher elevations, especially around like Prince William Sound in the winter, there's a lot of snow, and no, we don't bother digging 40-foot deep snow pits. We just dig snow cores. And we can do the same thing with the cores. We weigh the cores, and that picture in the middle is a snow core. To measure the ablation, we usually do these things at the same sites as the snow pits, and we have about 6 to 10 sites on each glacier that we measure at the same spots every year. And for the ablation, what we do is we use a steam drill, and we drill a really deep hole into the glacier. It just boil a bunch of water, and it comes out the end of the tip and melts the snow and ice. And we've got this nice long hole, and then we put a stake in there, and we can measure how much is sticking out there in the spring, and then we can come back again in the fall and measure how much is sticking out, and we can see how much snow we've lost and how much ice we've lost. So those are pretty simple. Measurements, really. And we take those measurements, like I said, at maybe 6 to 10 sites over a glacier. Although the older part of the record, generally they only had 3 sites, and we simply average those sites over the glacier area and come up with a time series of variability. And it's a time series of variability. It's not really a very good estimate of the glacier-wide number, but glaciers tend to have very strong patterns in their mass balance. So it does measure the interannual variability. It measures the difference from one year to the next really effectively. And if you look at the top panel of this figure, you can see that's just the raw cumulative difference. It actually makes it look like Wolverine Glacier here in Prince William Sound is gaining mass. But if we look at the digital elevation models, so maps that have surface information in them, surface elevation information, we can actually calculate a volume change. So we can see that the glacier is actually shrinking. And so you calculate the height change at every pixel, and then you sum those over the glacier to get a volume change, and you convert that volume to mass. And then you can check for a bias in your cumulative glacier time series. And once you calibrate that time series, then you have a really good idea not only of what happens from one year to the next, but of the total cumulative time series. And what you see at Wolverine is from the late 60s to the late 80s, if anything, the glacier actually gained a little bit of mass. There were a couple of really big winter balance years in there, a couple of pretty poor summers in there. And then since then, the glacier has really tanked. It's lost a lot of mass quite steadily. So at each of those glaciers, we also have a long-term weather station. So this is at Wolverine Glacier. This station went in 1967, and it really is the highest elevation station with a long record on the Kenai Peninsula. And you don't necessarily see the exact same patterns at sea level as you see up at higher elevations. And so it's useful to have a weather station that's right next to the glacier to try to give you some insight into what is happening on the glacier. This top panel, this is the temperature and the precip, but the red color is the average summer temperatures. And you can see that if you squint hard enough, it might be getting a little bit warmer in the summer. The pink temperature is the annual temperatures, and likewise, if you squint hard enough, you can see that it is getting a tiny bit warmer in the annual time period, but it's pretty subtle. But if you look at the same data in the middle panel in a slightly different way, if you look at it as how long is our melt season, there is a statistically significant trend there. And our melt season's about 10% longer now than it was in the late 60s. So those red dots are the length of the melt season. And that's overlaying on top of the mass balance record in blue. And you can see that most of the years in the second half of the record have a longer melt season than the years in the first half of the record. And what that really means is that we have a longer period of time when the precipitation that falls on the glacier is falling as rain rather than snow. And so that is impacting, it's that transition from rain, or from snow to rain, that's probably impacting the mass balance here at this glacier more than anything else. So we also use more sophisticated methods rather than just digging holes in the snow and doing simple averages. One of the things we've done a lot recently is we've been using high frequency radar, ground penetrating radar, to look at the spatial variability of snow. And the long-term record really just has those 3 measurement sites. More recently, we maybe have had 5 or 7 or even 9, but it's a lot different when you have 500,000 data points, and you can really learn a lot about what that distribution of snow looks like, what the drifts look like, what the scours look like, and where the bias is in that record of direct mass balance measurements. And it also gives you a lot more information about what your uncertainties are. So when you just have a couple of snow pits and then you come up with a glacier-wide estimate of what happened, and you have no idea what your uncertainty is. When you have 500,000 measurements, you can jackknife that data set hundreds of times and understand what the missing data that still remains, even in a data set like this, what that means for your uncertainties. And so one of the things that we found is we actually underestimate snow, not just at Wolverine, but at a number of our glaciers in the winter. And our uncertainties are pretty low when we use GPR. So here, we're talking about a couple percent of the total. But it's not just about winter balance. Having that snow thickness really allows us to use those, to use seasonal DEMs, so like surface elevations, usually from stereo satellite imagery, that are really high resolution, like from one fall to the next spring. If you look at that in a raw sense, it doesn't actually tell you that much about how much snow you have, and that's because the ice is always flowing. And in the accumulation zone, you have subsidence, and in the ablation zone, it's thickening. And so if you use the snow depth, what from the radar, then you can actually figure out what your emergence velocities, which is these green and pink figures over here on the right, are. And then you can go from there and use that to partition the DEM differences into mass balance and flow. And so here we've got annual mass balance distributed maps. This is from a PhD student who we're funding, Lucas Zeller, who's at Colorado State University. He just sent me these last week. And these are super cool. Really, nobody has distributed summer balances on glaciers anywhere in the world that are this kind of quality. And so this is going to yield real insights into why we seem to be missing so much ablation in those measurements that we've taken at those discrete sites. And just glancing at this, you can see that all the discrete measurements we make are in nice smooth parts of the glacier, and yet all the places that have complicated topography and lots of crevasses and steep head walls actually have a lot of extra ablation, which is something we suspected, but now we can actually quantify that. So as we move up to trying to think about glaciers on a more regional scale, obviously we're pretty limited with making direct measurements of just 3 glaciers, since there's 19,000 glaciers in Alaska. But to do that, we're really relying heavily on lots of remote sensing data. And I included this guy's mugshot in the background because Chris McNeil has really automated the process to go from optical high-resolution imagery from satellites, like the WorldView satellites and GeoEye satellites, to these digital elevation models, and then co-register the digital elevation models, not just with a couple GPS data points, but actually with all of the off-glacier data, line everything up. And he does it all automatically, and you come out with this stack of DEMs at the end. And so instead of just having a really time-consuming process where one person spends a lot of time to get out 1 or 2 DEM differences, we now have this automated pipeline, and his computer just makes a request and then gets a whole stack of DEMs back, and they're all lined up. And we're also using the same data to try to help a bunch of collaborators work with ISAT data to understand what's happening on thousands of Alaska glaciers, because ISAT samples portions of thousands of glaciers multiple times every winter. But if you only look at these partial strips by themselves, it's actually tricky to interpret what's going on. And so we're trying to sort of come up with conceptual models and then test them against these glaciers we have a lot more data on. And this is just a figure that I asked Chris to make a figure for this talk, and he spit this one out in about 5 minutes for me. And so this is just a long-term elevation change for Prince William Sound. And you can see it's about a 50-year difference. Most of the big glaciers have thinned by over 100 meters near their terminus over that 50-year period. And glaciers like Columbia have huge areas that have thinned by, I mean, there's parts of Columbia that have thinned over 200 meters. And a couple of glaciers have even thickened a little bit. And those are tidewater glaciers. I don't really have time to talk about tidewater glaciers, but they're super interesting too. But the vast majority of these glaciers have thinned, especially near their terminus. If we want to think about the way these glaciers are going to change in the future, it becomes a little bit more challenging. But the sort of primary control on glacier mass balance is really the hypsometry, which is the distribution of area with elevation. And in particular, what we're interested in is how much of the glacier's area is close to the current ELA. So how much of the glacier's area, if we change the climate just a little bit, is going to transition from an accumulation zone into an ablation zone? Or how much of the glacier's area could transition from accumulation to ablation zone just by thinning a little bit? And so what is obvious right away is that these areas that have really high elevations, like northern Prince William Sound, where you've got Mount Marcus Baker and Mount Thor and Witherspoon and all those cool peaks, they probably aren't going to change as much between now and 2100. They're still going to change. You know, notice that the smallest projected amount is 36 to 44%. So they're still going to change, but they're not going to change as much as some of these small glaciers at the periphery, which may more or less completely disappear. And another interesting spot is down here, the Sargent Ice Field over in western Prince William Sound. That doesn't have very high elevation. So even though they're pretty big glaciers, they're really large glaciers, and they get really high accumulation rates in the winter, those glaciers are really susceptible to changes in that snow-rain fraction because there's so much area that's really pretty low elevation on the scale of things. So another big project we have going on right now is thinking about fern. And fern, the reason that we need to think about fern is that is the big limitation between taking this fire hose of remotely sensed data that we now have access to and making sense of all of it. And the problem with fern is that you've got seasonal snow, which makes it through the year, and then we call it fern as it transitions from that seasonal snow into glacier ice. And that takes some time, and over time, it changes from a density of somewhere around 450 to somewhere around 900 for glacier ice. And so it's almost a factor of 2 change in density. And so fern that process is not super well quantified, maybe not well quantified at all for temperate glaciers like Wolverine or like most glaciers around Prince William Sound. And so understanding how much of that volume change signal that we see might be because of changes in the fern is kind of a little bit beyond our grasp right now. So we've been taking these long fern cores. This is an example here from Upper Wolverine Glacier. We've cored down about 90 feet, and we've measured the density of all these pieces, and we've identified summer surfaces where we can. This is an example of a nice dirty summer surface layer. So we take layers like this back, sample them, and look at them in the lab. And this is what the density data looks like. You can see it's a little bit messy. It gets more dense with depth, but there's some variability. And the reason it's variable is because this is what the fern actually looks like. There's sort of two competing processes in fern densification. One, the fern gets buried, and as it gets buried deeper, it gets sort of squished and compressed. But the other thing that happens is in the fall, the fern gets really cold. And then in the winter, it keeps getting colder, and it dries out completely. And then in the summer, as the seasonal snow on top of it starts to melt, you deliver a bunch of water to this thing that's kind of like a big dry sponge. And so it soaks up some of that water, and it freezes in because it's below the freezing point. Eventually, you add a bunch of ice, and that latent heat that's released as that water turns into ice warms the fern back up to freezing. And so then it's all temperate again at the end of the season. But how much ice you add really impacts the fern densities, and it means that it's a pretty heterogeneous process. So we've been measuring temperatures. We have a temperature string that's a tower in the background. And this plot is just temperatures through time with depth on the y-axis. It's an arbitrary depth, so I've added some interpretation. The green colors are right at the freezing point. So that's right at 0 degrees C. It's a mixture of snow or fern with a little bit of water, liquid water in it. The blue colors are below freezing, and the yellow colors are above freezing. So those yellow colors up in the top, and then the dark blue colors, that's actually where part of the temperature string is actually sticking above the snow surface. But those blue colors on the left edge, that's where you have some cold that's down below the snow surface, and that's where you're actually freezing water in. And you can see last year, the cold lasted till about the end of June. So we're also trying to measure fern compaction rates directly. We've got some collaborators from the University of Washington, Knut Christensen and Annika Horlings, and they've got this phase-sensitive radio echo sounding, how's that for a mouthful, radar system. It's got multiple frequencies, and so you can determine the distance between subsequent reflectors really precisely. And so we can actually make repeat measurements at the same site, and then we can calculate how fast that compaction term is actually acting. And so we can separate from the density both the compaction term and the internal accumulation, that growth of those ice lenses, that term. But let's get back to the water here really quickly. I'm running a little bit late, but we want to understand how long it takes for the water to get out of the glacier and then what it does down on the lower glacier. And so we've got a bunch of stuff with various collaborators up on the upper glacier to actually understand how the water is generated and how long it takes to get through the glacier. Time-lapse cameras with some other collaborators. Likewise, water at the bed of the glacier changes the velocities, so that's all kind of coming back to the water. And then we're sampling the water in a bunch of places. So we're trying to understand what are these chemical and physical properties of the water, because there really is very little data out there to constrain conceptual and physical models of how the system works. So these are some examples of conceptual models here, and then a pretty basic physical model that is trying to work at how this water looks different. This is Anna Bergstrom. She's actually got a paper that I think is just accepted now. Should be out later this summer, looking at sort of the seasonal variability on all these different water sources. and the spatial variability. So how does the water from the glacier compare to the water that's coming out of the forest, compared to the water that's coming out of a tundra stream, etc. And this is sort of the last main slide. So we've got Wolverine Glacier over here on the left. All the bright colors are glaciers. The blue thing, that's Kings Bay at the edge of Prince William Sound. And that black outline is all of the Neliwan watershed. And so we currently have about 50% glacier cover in Neliwan. And the projection for 2100 is that we would go all the way down to about 13%. And we're going to increase tundra, bare ground, and especially shrub, alder and willow areas. And we would expect real changes in the physical and chemical characteristics of the water coming out of this basin over that time frame. So thanks for coming this afternoon. And I just want to show you leave you with a little time lapse of Wolverine Glacier. This is the terminus of Wolverine Glacier in the foreground over 7 years of period. And those glaciers in the background, notice that they're also changing pretty dramatically. It doesn't look quite as impressive as they're a little bit further away. They're still changing. So thank you again. And I should have put my email on this slide, but yeah, thanks for your time this afternoon. My email is lsass@usgs.gov.
Thanks, Louis. We have a couple questions here for you. Have you noticed a trend with tidewater glaciers on glaciers like Bear, Valdez, Spencer that terminate into a lake with cataclysmic calving events, such as last year where Valdez Glacier calved almost 2 miles back from the toe? And are these correlated with recent climate changes and mass change that you've cataloged?
A trend, no. Lake calving glaciers, for several reasons, do have this tendency to calve back a little bit slower, but then have these major catastrophic events. And that's mostly because you're actually not mixing. You don't get as much warm water interfacing with these things once they kind of get limited in an estuary or actual lake back behind the tidewater interface.
Thank you. Hey, just real quick, what's the elevation of the Wolverine Glacier Weather Station?
It's 990 meters, so 3,000 feet.
3,000, okay. And I was just curious, has there been any changes in like the 30-year pattern of precipitation in specific months? That could be like, has that changed? Like, is there more precipitation at times of the year where there isn't freezing temperatures versus when there is? We haven't published a paper on this stuff, so I don't have like the best plots on the tip of my fingers, but informally looking at it, it does seem like there has been more precipitation in the winter, which is part of why I think is part of why the glaciers, at least in the early years, didn't retreat quite as much. I think we started to see more precipitation over the winter months in general, but there's also more in the fall. It seems like there's a little bit more seasonal pattern, a little bit less of a little bit of a shift in the seasonal pattern from what it was earlier. But in particular, it seems like we're getting more precipitation in the winter than we used to. Okay, well, that's interesting. Yeah, and then I think that's all for our questions, but there was just another comment about whether these slides would be available, and we will have this video posted on the princewilliamsound.org website probably in about a week. They'll be here at this Crowdcast event page for about a week. So yeah.
Yeah, thank you.
It looks like we posted your email address in the chat box there.
Great, that looks correct.
All right, thank you so much, Louis. Appreciate it. We're a little bit ahead of schedule, so we'll take a little bit of a break here, unless you have anything else to add.
Oh, I thought I was supposed to end at 4, so I was hurrying to.
You're doing great. Our schedule got a little mixed up. I think our next presenters will be at 4:10. So we'll take a quick break, and yeah, if you guys want to meet us back here at 4:10 for Milo and Charlotte's presentation on black bears research in Prince William Sound. Thank you.